Today, we stand at a turning point. For decades, military aviation has chased a single dream. This dream is true invisibility. We call it stealth. Engineers built special planes. They have strange shapes. They are covered in black, secret materials. Those materials absorb radar waves. A big bomber becomes a bird on a radar screen. This technology worked very well. It gave nations a powerful advantage. Planes could fly deep into enemy territory. They could strike without warning. No one could see them coming. The age of stealth seemed unstoppable. It changed how wars were fought. But that age is now ending. New technologies have emerged. We have created metamaterials. Not simple coatings, smart skins. They actively bend and redirect radar waves. They can make a plane seem like it's somewhere else. We also have active cooling systems. These chill the aircraft surface. They hide engine heat. Together, these advances make aircraft ghosts to traditional sensors, invisible to radio frequencies, invisible to infrared cameras. The old ways of looking for planes no longer work. Stealth's trick was hiding from waves, fooling radar and heat sensors. But we forgot a simple, powerful truth. An airplane must fly through the air. It cannot float in a vacuum. To fly, it pushes air aside. It must generate lift to stay aloft. That movement creates a disturbance. It leaves a trail, not smoke or light, a disturbance in the air itself. You cannot hide the air. You cannot stop it from moving. This fact is the key to a new way of seeing. So we must look for something different. Not the plane, its wake. The invisible scar it leaves in the sky. Not a new idea, but now we have the tech. We can sense tiny changes in pressure, tiny changes in temperature, tiny changes in density. This wake is a fingerprint. It tells a story. It reveals the path of the invisible plane. This is the new frontier, the end of stealth as we know it. We're no longer hunting the object, but its shadow in the atmosphere. Every object that moves through the air must push that air out of the way. Think of a boat moving through water. It creates waves that spread out behind it. An airplane does the same thing, but in 3 dimensions. The air is a fluid, just like water. As a wing slices through this fluid, it creates lift. This lift is what keeps the heavy machine in the sky. It is a miracle of engineering. But this process of creating lift is not perfectly clean. It has a side effect. It creates a powerful and lasting disturbance in the atmosphere. This disturbance is the airplane's invisible scar. The most significant part of this disturbance is the wingtip vortices. A wing works because there is high-pressure air below it and low-pressure air above it. The universe does not like this imbalance. The high-pressure air wants to move to the low-pressure area. At the tip of the wing, there is nothing to stop it. So, the air from below curls up and around the wingtip. This creates a powerful, swirling tube of air that spins off from each wing. These are the wingtip vortices. They are like 2 horizontal tornadoes trailing behind the aircraft, a permanent consequence of generating lift. These vortices are incredibly stable. They can persist in the atmosphere for many minutes after the aircraft has passed. The bigger and heavier the plane, the stronger and more powerful these vortices are. You may have seen their effects on a humid day. Sometimes you can see white trails streaming from the wingtips of a jet. That is water vapor condensing inside the low-pressure core of the vortex. But even when you cannot see them, they are always there. They are a fundamental signature of flight. Hiding a plane's shape is one thing. Hiding these powerful tornadoes of air is impossible. This violent swirling of air is a massive signature. It is a clear sign that something big and heavy has recently passed through that patch of sky. The air is left spinning and churning. This is not a subtle effect. For a large aircraft, these vortices can be dangerous to other planes that fly through them. They contain a huge amount of energy. While stealth technology has focused on hiding the plane's metal body from radar, it has completely ignored this massive atmospheric disturbance. It was a problem that designers could not solve. So they ignored it. But physics does not ignore it. The scar remains in the sky, waiting to be seen. The wingtip vortices do more than just spin the air. They also change its properties in ways we can measure. One of the most important changes is temperature. This happens because of a simple law of physics. When gas pressure drops quickly, temperature drops too. This is called adiabatic cooling. You've seen it yourself. A can of compressed air gets very cold when used. The same thing happens in the core of a wingtip vortex. The center is an area of extremely low pressure. Air sucked into this spinning tube sees its pressure plummet. That sudden drop makes the air cool dramatically. The vortex air can be several degrees colder than the surroundings. That creates a long, thin tube of cold air stretching for miles. It is a thermal trail, a fingerprint in cold. A stealth plane can hide engine heat, but it can't hide this cold trail. The trail also alters density. Cold air is denser than warm air, but low pressure in the core reduces density there. So you get a low-density, low-pressure core surrounded by swirling air with varying densities. The atmosphere becomes a messy, complicated region of temps and densities. This complex pattern is unique to the aircraft's passage, a signature that cannot be erased. The wake is a distinct structure with measurable properties, a thermal and density fingerprint. This fingerprint lingers long after the aircraft is gone. It's a clue. Traditional infrared looks for hot spots like engine exhaust. It misses cold trails. We need new sensors. We need a new way of looking at the sky. We need tools that can see subtle changes in the air itself. The physics gives the clue. The key to seeing this invisible wake is a phenomenon called Bragg scattering. This sounds complicated, but the idea is simple. It's about waves bouncing off a structured pattern. Imagine throwing pebbles into a calm pond. Ripples spread out evenly. Now picture perfectly parallel lines on the water. Ripples interacting with those lines in an organized way. Bragg scattering is like that, but with radio waves and the structured air of a wake. A vortex's regular swirling pattern acts like a crystal. It gives a predictable scatter pattern. We don't use one big dish. We use many smaller transmitters and receivers spread over miles. This is multi-static sensing. Some antennas transmit low-power radio waves. Those waves blanket a huge volume of sky. They're too weak to reflect off stealth metal, but they don't need to be. They're just illuminating the air. Other antennas, miles away, only listen. They listen for faint, scattered signals. They track tiny changes in the sky's background noise. The magic is combining those weak signals. Faint echoes from a turbulent wake make a unique interference pattern. The vortice's regular structure, spacing and rotation, causes radio waves to scatter in a specific way. That's the Bragg peak, a sharp spike at a particular angle and frequency. It stands out from atmospheric noise. Finding it is like seeing a shimmer in the air. It's a telltale sign of a structured disturbance. This technique is incredibly sensitive. We're not hunting a strong metal reflection. We're hunting a subtle, coherent pattern in the air. Like hearing one clear note in a noisy room. Hard, but possible when you know the note. Wingtip vortex physics gives the note. Bragg scattering gives the ear. This radar doesn't see the plane. Detecting a small shimmer of Bragg scattering at a single point in the sky is only the first step. It tells you that a wake is present right now, in that location, but the aircraft that made it is already gone. It might be miles away. To find the plane, you need to connect the dots. You need to reconstruct its path. This is where artificial intelligence becomes the essential partner to the new sensors. An AI program acts as a digital detective. It takes in thousands of these faint, scattered data points from all the different receivers and begins to piece together the puzzle. The AI is trained on vast computer models of atmospheric physics. It understands how a wake behaves over time. It knows that a vortex starts out strong and well-defined and then slowly loses energy and breaks apart. This process is called wake decay. The AI has learned to recognize the signature of a fresh vortex versus an old one. It can look at the strength and clarity of the Bragg scattering signal and estimate how long ago the aircraft passed that point. A strong, sharp signal means the plane was just there. A weak, fuzzy signal means the wake is older and has started to dissipate. By sampling the sky in many places at once, the system can find multiple points along the wake's path. The AI then plays a game of connect the dots, but in 4 dimensions, 3 dimensions of space and 1 of time. It might get a strong hit here, a weaker one a few miles back, and an even fainter one further back. The AI then calculates the most likely flight path that would create this pattern of decaying wake. It can draw a line through the sky, showing where the plane has been, and the end of that line, where the wake is freshest, is where the plane is right now. This process is not simple. The atmosphere is a chaotic place. Wind, weather, natural turbulence. But this is what modern AI is built for, finding meaningful patterns in noisy, complex data. The AI can filter out the random gusts of wind. It can account for how weather fronts might distort the wake. It constantly updates its model of the atmosphere and compares it to the incoming sensor data. The result is a moving track on a screen, showing the real-time location of a target that is completely invisible to every other sensor. The ghost is no longer a ghost. Imagine a high-value military command center. It is protected by the best defenses available in 2026. A network of powerful X-band radars constantly scans the skies. These radars are designed to find small targets. These radars are designed to find fast-moving targets. Today, they see nothing. The sky is clear, but an enemy has launched a stealthy attack drone. This drone is coated in the latest radar-absorbent materials and uses advanced metamaterials to appear invisible. It is flying low, using the cover of a scattered cloud layer to approach its target. To the X-band radar, the drone does not exist. It is a ghost. However, a different kind of defense system is also active. It is a multi-static atmospheric sensing grid. Dozens of small, low-power transmitters and receivers are scattered across the countryside, disguised as cell phone towers or hidden in the landscape. They are bathing the entire area in a soft wash of radio waves. They are not looking for the drone. They are watching the air. As the drone flies, its wings create powerful vortices. When the drone passes through a puffy cumulus cloud, it does something interesting. It carves a perfect tunnel through the water droplets. The powerful spinning of the vortices pushes the cloud aside. One of the ground receivers detects a strange pattern. The signal passing through that specific cloud is no longer random. It shows a faint but clear Bragg scattering signature. The AI system flags this anomaly. It knows that vortices in a cloud create a highly structured disturbance. Other receivers are queried. They too begin to detect faint distortions in the air along a specific line. A fire control solution is calculated based on the wake's trajectory. A missile is launched not at the drone, but at the predicted location at the very tip of the fresh wake. The invisible drone is destroyed by a weapon guided by the air it disturbed. The invisible is made visible and vulnerable. The failure of the old system and the success of the new one comes down to a basic difference in philosophy. Legacy radar, like the X-band system, operates on a simple principle. It is like shouting in a dark cave and listening for an echo. The radar sends out a powerful pulse of energy. It then listens for that energy to bounce off a solid object and return. The bigger and more metallic the object, the stronger the echo. Stealth technology was designed specifically to defeat this principle. It works by preventing the echo from ever coming back to the receiver that sent it. Stealth planes use 2 main tricks. First, their shape is made of flat angles. Angles reflect the pulse away, like a tilted mirror sending a flashlight away from your eyes. The energy isn't destroyed, it's just sent elsewhere. Second, the plane is coated in radar-absorbent material, RAM. RAM is like a sponge for radio waves. It soaks them up and turns them into a tiny bit of heat. To the radar, the sky looks empty. The new multi-static atmospheric sensing system doesn't play that game. It doesn't care about echoes from the object. It assumes it won't get one. Its target isn't the plane. Its target is the atmosphere. The system sends energy from one spot and listens from many other spots. That's the crucial difference. A stealth plane can deflect energy away from one receiver. It can't angle away from dozens of receivers spread in all directions. Some scattered energy will be picked up. This is why the new system succeeds where the old one fails. It changes the rules of the game. Stealth solves direct reflection. The new system doesn't look for direct reflection. It looks for how the plane's wake disturbs the air. It's not fooled by shapes or paint. It's looking at the air. X-band radar shouts and waits for an answer from the plane. The wake left by an aircraft is more than just a line in the sky. It is a rich source of information. An expert can look at the wake of a ship on the ocean and tell you a lot about the vessel. Estimate its size, estimate its speed, estimate its shape. The same is true for the invisible wake of an aircraft in the sky. The AI-driven sensing system does not just detect a path. It reads the details of that path. It analyzes the characteristics of the vortices to learn important details about the aircraft that created them. This turns a simple detection into a detailed intelligence report. The first and most important clue is linked to the aircraft's weight. Lift is the force that opposes gravity. An aircraft must generate lift equal to its own weight to stay in level flight. The creation of wingtip vortices is a direct byproduct of generating lift. Therefore, the heavier the aircraft, the more lift it needs to generate. The more lift it generates, the stronger and more powerful its wingtip vortices will be. A heavy bomber will create a massive, violent, long-lasting wake. A small, lightweight surveillance drone will create a much weaker, more delicate one. By measuring the energy, the aircraft's speed is also encoded in the wake. The distance between the two counter-rotating vortices, the left-the right, is roughly equal to the wingspan of the aircraft. As the vortices trail behind the plane, they begin to interact with each other and the surrounding atmosphere. They slowly drift downwards and apart together, depending on atmospheric conditions. The speed of the aircraft affects the initial spacing and structure of this wake. More importantly, by tracking how quickly the signature moves from one point to another, the system can directly calculate the aircraft's ground speed with incredible accuracy. This ability to analyze the wake provides critical tactical information. Is the detected object a heavy bomber loaded with weapons or a lightweight fighter on patrol? Is it a fast-moving jet or a slow-moving drone? The system can distinguish between them. For example, it might detect a very heavy wake signature moving slowly. This could indicate a large transport plane. The rise of wake detection marks a fundamental shift in the cat-and-mouse game of aerial warfare. For half a century, the focus was on shaping materials. The goal was to create a design that was aerodynamically efficient and electromagnetically invisible. This led to the iconic, angular shapes of stealth aircraft. We optimized the object. But wake detection changes the focus from the object to its interaction with the environment. The very geometry of stealth, designed to defeat radar, is becoming obsolete. The future of stealth is not about shape, but about mastering physics on a much deeper level. This will trigger an immediate and intense arms race. On one side, engineers will build more sensitive, intelligent wake detection systems. They will deploy vast networks of ground-based sensors. They will deploy air-based sensors. They will deploy space-based sensors. They will refine AI to pull ever fainter signals from atmospheric noise. They will learn to read subtler clues from the wake. The goal: make the sky completely transparent so nothing can move through it unseen or untracked. On the other side, aircraft designers face wake mitigation. How do you stop a 200-ton aircraft from disturbing the air? The ideas sound like science fiction. Perhaps future aircraft will have active wing systems that inject plasma to break up vortices as they form. Maybe they will use focused energy or oscillating control surfaces to actively cancel the wake like noise-canceling headphones for aerodynamics. These techs are far more complex than painting a plane. They require rethinking how a wing works. Ultimately, this arms race can't be won by clever engineering alone. It's a race against the laws of physics. An object moving through a fluid will always displace that fluid. Generating lift always has consequences. You cannot jam physics. You cannot make the air ignore the wing that passes through it. New tech may reduce or mask a wake, while other tech finds the remaining traces. The era of true invisibility, if it ever existed, is over. The future of aerial dominance belongs not to those who hide best, but to those who best see and understand the atmosphere's invisible battleground. This is the end of invisibility, and the beginning of a new way of seeing. In a world of perfect camouflage, the laws of physics are the only sensors that cannot be jammed or fooled.